Hi folks, we're going to take a look at page 389, number 11. So here they give us three forces with magnitudes 3, 4, and 5 newtons, and they're acting in equilibrium, and they want us to find the angle between the smallest and largest forces. Okay, so because these three forces are acting in equilibrium, it means that if I were to add them tip to tail, that they should form a closed triangle. Okay, so let me just draw a diagram here. So since they don't give me any directions, I can just draw them anywhere I like. So I've got this 5 Newton force, and then I'll put the second largest one there. This will be my 4 Newton force. And then my third one I know has to connect the triangle. Okay. Now, knowing that the 3, 4, 5 triangle is, of course, a right angle triangle, but I'm actually not going to assume that's the case. I'm going to solve the problem more generally, just so that it's not tied to being a right angle triangle. So we know that we have this situation here, and we want to find the angle between the smallest and largest forces. So here is the smallest and largest. So I know I'm going to be looking for this angle, which I'll call theta. But right away I want to remind you that what I've presented here is not the angle between the vectors, because the angle between the vectors, of course, is when they're placed tail to tail, and here that's not how they're placed. But this is the one I'll find, and then that'll help me determine the angle between them, and we'll look at that later. Okay, so here this is a cosine law problem, so we've got theta is just cos inverse of, okay, and what do I have? Well, its opposite side is 4, so that's going to be 4 squared minus 3 squared minus 5 squared over negative 2 times 3 times 5. Okay, so let's calculate that here. So what do we have? We have inverse cosine, open up the top. So that's 4 squared minus 3 squared minus 5 squared. And then open up a bracket for the bottom, negative 2 times 3 times 5. Okay, and we've got 53.13. Okay, so again, this is the angle in this triangle, but this doesn't represent the angle between the two vectors. So in order to find the angle between the two vectors, I need to move them so that they're tail to tail. So what I'm going to do is I'm going to take this vector here, and I'm just going to move it over so that I place it tail to tail with that with the tail of the 5 Newton vector. Okay. So of course I can do this because vectors are movable. There's my 3 Newton vector. So this is the angle that I'm looking for, so that the 3 Newton vector and the 5 Newton vector are placed tail to tail. And again, because I've got this straight line, I know that the angle phi, which is what I'm looking for, is just going to be 180 minus 53.13, which of course will give me, I guess I should be able to calculate that on my own, but let's use a calculator. So minus 180, so 126.87. Okay, so just to recap, because these vectors were in equilibrium, that's why I had the closed triangle, so I was able to use trigonometry. Now, while I did recognize this as likely being a right angle triangle, I just pretend that I didn't know that, just solved it as I normally would with cosine law, but then realized that the angle I got was not the angle between the vectors. I had to move one of them to place them tail to tail. Okay, that's it for this one.